Hello, welcome to this video. So in previous videos I've gone through some of the beginning of quantum field theory for a gifted ammeter. If you liked those videos I would really recommend purchasing the book. But these videos just give a broad overview of the material covered in there with kind of my own additional pieces of explanation as to how it extends sometimes into other branches of physics, or how we can interpret the mathematics. But this is a broad overview of quantum field theory for the gifted ammeter, and today we're looking at part 3 of this overview, which is going to be the first part of the classical underpinning of quantum field theory, where we could be building in parts 1 and 2 of this. So you could think of today's part as the part 3A, if you like, and another day's part as 3B. But in part 3, we'll be building up to describing the equation of motion, which says how quantum fields should behave. So it's kind of like Newton's equation for particles, but instead it would be an equation for fields. And in that we'll be talking about the Euler-Lagrange equation for fields. But today we're just doing part 3A, if you like, where we'll be introducing the idea of the Lagrangian, which we use in quantum field theory. We use something similar called the Lagrangian density, which is quite similar to the Lagrangian, and we'll be talking in this part about Hamilton's principle of least action, which governs how particles behave according to Newton's laws, but which is very applicable to quantum fields as well. So, ironically, for a video on quantum field theory, there won't be any quantum in this video, nor will there be fields, but in the next video we'll extend what I have here to fields, and then in future video we'll look at quantizing those fields. So, the key bit of maths we need for this video, which is trying to get to a fundamental equation, in some senses more fundamental than Newton's laws, which describe how particles behave. We want a really fundamental description of how particles behave in something that is a lot more simpler in some ways, but in other ways more abstract than Newton's laws. To do this, we're going to make use of something called functionals and functional derivatives. So firstly, you might ask, what is a functional? Now, you can create a very neat comparison between functions and functionals. So a function is something that when you give it an input, which is usually a number, although we can have functions of vectors, but typically functions take a number as an input and they will output another number. So we can think of it as almost like a map between two sets of numbers, between an input set of numbers and an output set of numbers. And this map is described as a function. And we can visually see a function as the reg line here, and this reg line has each coordinate has an x component, which is the input number, and y coordinate, which is the output number. And a function is just something that takes the input and gives you an output, and you can plot it on the graph like this. And so we're fairly familiar with functions, and I've gone over it quite quickly because functions are something you use a fair bit in GCSE, but you study in particular depth at A level. So functions are fairly well known. Functionals much less so. So A functional is something that takes in an entire function and returns a number. And this is kind of hard to visualize, but I've done my best here, where to the left image, you can see I've got along the x-axis, each point along the x-axis represents a particular function, and then this red line you can get by essentially doing something to the entire function and outputting a number, and if you plot the function against the output you can get a curve. And the functional is generally described, generally represented as a curly letter, and we use a curly letter because if we use capital F, we might be thinking we're talking about Fourier transforms, which I made from a previous video. If we use a lowercase letter, we might be thinking that we're talking about applying another function onto the original function, so doing composite functions. And so to make it clear that we're talking about a functional, we use a curly letter. And a functional is something that takes in an entire function and returns a number. Now, it might sound like this is a very abstract thing, taking an entire function. But actually, you've seen functionals before if you've done A-level maths, and you would have seen even more of them if you've done further statistics and further maths. And they pop up a lot, it's just often we don't really recognise that they are functionals. But I'll give examples of functionals on the next slide. And as a reminder, a functional is something that takes an entire function and returns an output number. So the first functional that you probably have heard of, if you've done A-level maths or beyond, is the functional which returns the area under a curve. So when we're finding the area under a curve, we are actually using a functional, because the input is the entire function. Well, strictly it's the entire function between 2 points. But we could be integrating when we're finding the area from x equals minus infinity to x equals infinity, so we could be taking in the entire function. So the input could be an entire function, or at least it is a segment of a function, and then the output is a number representing the area between the curve that represents that function and the x-axis. So for example, our input function could be f of x, and if we want to find the area between a and b, we take in the entire function between those x-coordinates and we output a number, and therefore, this, because it's a number, the area of a curve is always, area under a curve is always a number, we are dealing with a functional. And this functional just looks like the integral of f of x dx, because we consider the integral to be visually interpreted as the area under a curve. So you've probably used functionals before. So often when we're dealing with functionals, we're either using the derivative operator from calculus or the integral operator from calculus, and usually it's the integral operator. So really, whenever you've seen an integral, because the thing that goes into an integral is a number but is a function, you are probably dealing with functionals, because you're inputting a function and you're getting out a number. Another kind of related functional is the one that we use to find the average value of a variable. So say you have a variable changing over a period of time, and you want to find the average of that variable. So firstly, you need a function representing how that variable changes over time. And then as an output, you'll get a number representing the average of the variable, and then the functional looks something like this, where we're finding the average of the variable between t equals 0 and t equals tau, that curly t is a tau, and the variable that we're finding the average value of is k, and k is a function of t because k is varying with time. So what I tried to show so far is that as strange as functionals at first appear, you have indeed seen functionals before. And before we go on to using them very shortly to reformulate Newton's second law of motion to get something really fundamental that even quantum fields obey, I would just like to talk about something related to functionals called the functional derivative, or sometimes the variational derivative, which is about how we differentiate functionals. So differentiating functions you're probably clear on if you've done A-level maths or beyond, but if we could use functionals and we want to do calculus with them, then we would like to know how to differentiate functionals themselves. And that's what we'll be looking at in the next slide. So, to differentiate a functional, we do something very similar to what we do when we find the derivative of an ordinary function. So I've shown a graph of a functional here. This red line is kind of the functional. And the way we find the derivative or the slope of this functional is we take 2 points along the x-axis and we look at what's the functional for these 2 points. And then we take the limit of kind of the gradient between those 2 points on the graph as those points get closer and closer together. And so that's what we do when we're taking the ordinary derivative. We do the same when we're taking the functional derivative. It's just now the x-coordinates of these 2 points are functions, they're not numbers. So it looks a little different. But the idea of how we find the instantaneous derivative of a curve is exactly analogous to how we find the functional derivative. And I've given a formula for the functional derivative here, but it essentially comes from finding the gradient of the average gradient, if you like, of the curve, or a gradient of a line between 2 points, and then finding the limit as those 2 points get closer and closer together. It's just these 2 points have an x-coordinate which is a function instead of a number. So for example, functions like f of x prime, and then a small amendment to that function a little bit later. Now, what if we have one of the x-coordinates of points being f of x prime? You could ask, well, what should the function relating to the x-coordinate of the second point be? And for convention, we take the x-coordinate of the second point to be a similar function to the x-coordinate of the first point, but we just create a tiny spike in that function to make the 2 points represent, the x-coordinate of the 2 points represent slightly different functions, but similar. Because what this delta function is doing in our variational derivative here is it's essentially creating a tiny spike. And as we find the limit, as epsilon goes to 0, this spike is going to get smaller and smaller and smaller, until the two functions become the same, because essentially we're taking the limit where the 2 points meet and become a single point. And remember, the x-coordinate of the points are represented by functions. So if the coordinates of the points meet, then the functions meet. And that's what happens as we take epsilon goes to 0. The amplitude of this peak goes to 0, so our two functions become the same thing. And what we can see from this curve is that this curve clearly has maximum and minimum points. Now, if I had a function, I would say we get a maximum or minimum point, else called a stationary point, when the derivative is 0. So similarly, for a functional, we get a maximum or minimum point or a stationary point of the functional when the functional derivative is 0. So we can summarise that by saying when the functional derivative is 0, that is when our output number is either at a maximum or minimum, a local maximum or minimum. We have maximised or minimised the functional. So now we talked about functionals and functional derivatives, and as promised, we're going to use them to rewrite Newton's laws. Well, Newton's second law in particular. So, Newton's second law can be written as the equation here, where we have mass times acceleration, and remember acceleration is the second derivative of position with respect to time, is equal to the force. But the way we think about force classically is a force has a potential associated with it, and the potential and force are associated such that the force is minus the derivative of the potential. So F equals ma becomes m times the second derivative of position with respect to time is equal to minus the first derivative of the potential with respect to space. So quite wordy there, but this equation is essentially Newton's second law, just written in the kind of form you would see it at universities, etc., instead of the form it's usually seen at in A-level physics or before that. However, as can be shown in the book Quantum Field Theory for the Gifted Amateur, which these series of videos are based on, goes into immense detail on, but I've given enough here where you can actually work out, although it is quite tricky, but you can, using what I've given here, show that the above equation is equivalent to the bottom equation, where we have, in the bottom equation, the partial derivative of the average value of the potential. Sorry, not the partial derivative, my mistake, I'm getting confused with derivatives. The functional derivative of the average of the potential with respect to space is equal to the functional derivative of the average of kinetic energy with respect to space. And remember, averages, the way we calculate averages involves functionals, so we can meaningfully talk about the functional derivative of the average value of potential energy or the functional derivative of the average value of kinetic energy. Now, the two equations are equivalent. I'm not going into the proof here, firstly because the book does a brilliant job, and secondly there isn't really any more physics than what I have already shown, nor is there really any new maths. It's just a lot of computational stuff goes in to transform the first equation into the bottom equation. But the two equations are equivalent, and what we've done here is we've turned a description of Newton's law from something that involves functions and ordinary derivatives into something that involves functionals and functional derivatives. And so now we are ready for our last slide, where we will get to a beautifully simple equation that summarises Newton's laws, but in terms of functionals and functional derivatives. So we start with Newton's law in terms of functionals and functional derivatives mentioned on the previous slide. And we can kind of, if you like, factor the functional derivative operator out. I mean, really, because it only works because it's a linear operator. Strictly, we can't really factor an operator out. But the maths works. And it's fairly clear that it, at least it's not surprising, that the second equation would turn into the top equation. It's just a bit rearranging. And then we define something called the Lagrangian, which is T minus V, so that's the kinetic energy minus the potential energy. And we also define an action. And the action, well, there's two ways to think of it. We can either think of the action as the output of the functional, or we can think of it as being the functional itself. In the same way that when you represent a curve as y equals f of x, you can think of y as an output, or you can think of y as the function f of x. So similarly here, we can think of the action as the output of a functional or a functional. But we've got here, nonetheless, a functional because we've got an integral of a function. And the integral of a function, as we described before when talking about the area under a curve, is indeed a functional. And now, if you use the equation we had before for the average of a variable as it varies over time, you can show that because we've established that the functional derivative of the Lagrangian, well, we've established that the functional derivative of the difference between average kinetic energy and average potential energy is 0, then due to our definition of the Lagrangian, you can show that this implies that the variational derivative of the action with respect to space is 0. And this is Hamilton's principle of least action. And so we can think of Newton's second law as an equation that arises because particles are trying to minimize the kind of local output of a functional. They're trying to minimize the value that we get when we take the functional. And so it's called Hamilton's principle of least action because it's particles trying to minimize the action. And so this simple equation involves some quite abstract concepts like functionals and functional derivatives, but it's beautifully simple and it captures all of Newton's second law. And this is actually an equation that describes motion, which with a bit of an adaptation we can apply to fields in space-time, and so quantum fields obey something very analogous to Newton's second law, but it's written in terms of Lagrangians, and it relates in the end back to Hamilton's principle of least action. And that will be what we're looking at next time. I know this video has been rather long, but that's because functionals and functional derivatives is a challenging topic, but I hope you've enjoyed this video, and I'll hopefully see you for the next one soon.